Okay, we're in mission 1, inertia and Newton's first law. So answer this question. Pause the video and answer the question. So it shows the answer C because Newton's law applies to both moving and non-moving on objects, right? An object at rest stays at rest. An object that's moving moves at a constant speed in a straight line. Okay. There it is, question 2. Answer this question. Pause the video. So you should read them one by one and reject those that are wrong and pick those that are right. Only E and F are correct. It maintains its state of motion, that's right, there's no change. It keeps its velocity, either a constant velocity, that means a steady speed and a constant direction, or if the velocity is 0, it stays at 0. It doesn't accelerate, it doesn't speed up or slow down, it doesn't come to rest if it's not at rest, it doesn't eventually stop if it's moving. So these are a good way to learn, right? You go through each statement and either confirm it as being true or not true. Okay, pause the video and answer this one. Inertia depends only on mass. It does not depend on speed, right? Inertia and mass are synonymous. Okay, try this one. Whoops, I mistakenly checked and it forwarded. So the answer was C anyway. If you go back, you'll see that the answer was C and the others are incorrect. So take a look at this one. So we've seen this one before. Inertia does not depend on speed. Inertia only depends on mass. So Mac is right. Inertia is a force. Inertia is not a force. Inertia is mass. Okay, pause and read and answer. So A is the only correct answer. If it stops at the bottom, it has to be a force to stop it. An unbalanced force is not required to keep an object moving. The natural tendency of an object is to move in a straight line at a constant speed or to stay at rest, and the presence of inertia is what keeps it going, not causing it to stop. All right, pause and answer. Okay, for some reason these questions are repeating. We've seen this one before. Try this one. So A and D, inertia is not a force. Inertia is mass, right? Inertia is not a force. Okay, pause and answer. Inertia only depends on mass. It does not depend on velocity. And be careful, sometimes it's least to greatest and sometimes it's greatest to least, so read carefully. So this is least, B, C, A, D, least to greatest. Try this one. Make sure you read all the statements and see why they're wrong. And so all objects have inertia because all objects have mass. Try this one. Remember, pause and answer before you look at my answer. Once again, remember to look at each statement and reject it as true or false, because finding the false statements is as important as finding the true ones. So here, maintain the state of motion. That's the first law. Keep its velocity, whether zero or non-zero. The velocity doesn't change. It will not eventually stop. It will not accelerate. It will not either speed up. And that one's also untrue. Okay, try this one. Pause and return. Once again, inertia is not a force. It only depends on mass. So least to greatest, we start with the least, and we go to the greatest. Done. Okay, we're starting mission 2, balanced forces. I'll remind you, I did forget to mention, but there's a table of contents at the end of this video. So if you want to find specific missions, go to the end of the video and it'll tell you where each mission starts. Finding individual questions, you're going to have to scroll through. So pause the video. Oh, yes. We divide problems into 2 categories. Balanced forces, where the acceleration is always 0, and the velocity 0 and non-zero will be constant, and unbalanced forces when you have an acceleration. So the category of balanced forces is the category that covers situations where the law of inertia, or Newton's first law, holds true. So answer this question and then come back. We've seen this question before. The 2 true statements for a balanced force situation are A and E, and the others you should recognize as all being false. Okay, try this one. Okay, here's a very tricky question. Notice the answers I picked. Most of you, maybe all of you, will get it wrong the first time you see it. So based on this information, which objects could be moving to the right? You see my answer. They're all true. Okay, let me explain. This object, the forces are balanced, so this could be moving to the right at a constant speed. Here they're not balanced. If this object is moving to the right, it would be accelerating. Here, all the forces are balanced, so this object could be moving to the right at a constant speed. Here the forces aren't balanced. Okay, so how could this be moving to the right? It's moving to the right and slowing down. Right, moving to the right and slowing down. And this one would be moving to the right and speeding up because there's a net force in the same direction. Notice if there's a net force opposite the motion, an object can move opposite, but it's going to be slowing down. So all the answers are true. Okay, pause and answer. Okay, another tricky question. So the situation's balanced, so we know what that means, but you can be absolutely certain. So it's a trick of language in a way. Absolutely certain. Has an acceleration of 0? Yes, we can be absolutely certain. Has a velocity of 0? Well, it could have a velocity of 0, but we're not certain. Is accelerating? It's definitely not accelerating. Is it rest? It could be balanced and at rest, but we're not certain just because it's balanced. Is not accelerating? Yes, we're absolutely certain it's not accelerating. Is moving and moving straight? Could be, but we're not certain. Could be, but we're not certain. So it's only A and E. Notice it's kind of a tricky language situation. Okay, here's a new type. Read the instructions carefully. We're relating free body or force diagrams to a motion diagram. Read it over carefully and answer it before you listen to me answer it. Since this is the first one of this type, let's go through it slowly. So it tells us it's moving leftward. So an object is going to the left at a constant speed. So if this object would be going to the left and accelerating, it would be like an object on a table where the normal and the gravitational force were balanced and it would be being pushed to the left. It would be accelerating. It wouldn't have a constant speed. This would be like a similar object where it was being pushed, but there was a little bit of friction. Again, this force is bigger than that. It's not balanced. It would have to be accelerating. These forces are all balanced. So this could be an object moving to the left at a constant speed. In this case, it would be an object. Notice this is the normal force, the table. This is the gravitational force. This is, say, me pushing it to the left, and this would be friction acting opposite. So these forces are balanced. There are forces in this direction, but it would be moving at a constant speed. This one would be like a frictionless cart on a flat surface. It would just be moving to the left without any force to the left, right? As long as it was moving to the left, it would continue moving to the left. So this is a frictionless cart where there's a normal gravitational force, a normal force, and no force at all in the direction of motion. Now, if that confuses you, yes, somebody pushed it to get it started, but once my hand leaves the object, the frictionless cart on a flat surface, it's going to go at a constant speed in that direction. So C and D are correct. And E, if it were moving leftward, what would it be doing? That would be like a cart that wasn't frictionless moving leftward, and there would be friction slowing it down. So notice I'm not just getting the right answers, but I'm thinking through each diagram, why it's right, why it's wrong, and importantly, what kind of situation each one of these would be. Those are the kind of questions I will ask you on a quiz beyond just the MOP questions. So if you didn't get everything I said in the last 2 or 3 minutes, go back over and listen to it carefully. This will be an important part of your learning experience for this week's assignment. Let's check. Good, I was right. Okay, read carefully, answer, and then come back. Okay, so only C is correct. Read the other answers. Remember, this is the free body diagram of this situation. Once the ball leaves my hand, the only force is gravity. There's an unbalanced force, and when the ball goes up, it's accelerating down, and when it comes down, it's accelerating down. There's always only one force and one acceleration, and it is unbalanced. Let's check the answer. Okay, read this one and answer and come back. Note, while the ball is going around the surface, the edge of the rim is pushing it toward the center. So as long as it's touching the rim, there's an unbalanced force toward the center. Once it leaves the edge, there's no longer any force on it. It's going to go in a straight line at a constant speed. It's not going to continue to curve because there's no force. And it's not going to swing out. It's just going to go straight. Let's check the answer. Okay, next problem, read and answer. Make sure you go through every possible answer and convince yourself why it's not true. That's an important part of your learning process, is to identify the wrong answers. And remember, and watch the must statement, the must capitalized. That's an important part of the logic of what makes some answers wrong that might otherwise be correct. Let's check. Okay, read, answer, and come back. We've seen all these choices in previous questions. Here we have a situation where the forces are balanced. And so only E and F are true, but make sure you know why the others are not true. Okay, check and come back, answer and come back. Okay, the key word here is could. It's not must or might. It's could be moving to the right. but it's a constant speed. So that tells us the forces have to be balanced. So A is balanced, B is balanced, C, D, E are not balanced. So it could not move at a constant speed if it were C, D, or E. A and B could be moving to the right, it could be moving to the left, it could be at rest. We're not sure of any of those, but it could be moving to the right. Notice the language is also an important part of the question. Try this one, answer, and come back. Okay, it would be easy to mess up here. This says could be moving to the right, but there's nothing about constant speed, okay? So now they all apply, right? This could be moving to the right at constant speed. This could be moving to the right at a constant speed. This could be moving to the right and accelerating. This could be moving to the right and slowing down, and this could be moving to the right and slowing down. So they all could be moving to the right. Try this one and come back. So two things to notice. Not balanced. Okay, so it's accelerating, right? And be absolutely certain. So those are two conditions we got to fulfill. And we are absolutely certain that if the forces are not balanced, it's accelerating. All the others are wrong. You can go through them one at a time. That can't be true. It can't have a velocity of 0 and be accelerating. It can't be moving at a constant velocity. Moving in a straight line. It could be accelerating in a straight line, but we can't be absolutely certain, right? So the only one that we can absolutely certain about is G. Okay, try this one. Once again, be careful of the language. So we have balanced, but we have to be absolutely certain. So if it's balanced, it might be at rest, but we can't be certain. Has an acceleration? Yes, it must have an acceleration. So it could be moving in a straight line, but we're not certain. Moving with a constant velocity, we're not certain. It could be at rest. Has a velocity of 0. We can't be absolutely certain. Yes, we can be absolutely certain it's not accelerating, and that's obviously not true. Okay, we'll check our answer. Good. Okay, now we've moved on to mission 3, which is unbalanced forces and accelerations, right? We know what happens with balanced forces, no acceleration, and unbalanced forces, we must have an acceleration. So answer this question and come back. So if an upward moving elevator is slowing down, there must be a net force down. So this can't be true because there's no gravity force. This has a bigger force down, the gravity force, than the tension force pulling the elevator up, so this could definitely be true. The upward force is bigger, it would be accelerating up, or coming down and slowing down. This is balanced, it would have to move at a constant speed, and this is balanced, it would have to move at a constant speed. So B is the only one that could be correct here. Okay, check this out and answer the question and come back. Okay, the net force is up, so if the person is falling, they would be slowing down. Right, so the skydiver will have an acceleration that is directed upward. If the skydiver is falling and slowing down, the skydiver will continue to fall but will now slow down. The net force is up. The skydiver will begin moving upward. No, we know that doesn't happen because what happens is as the skydiver slows down, this resistive force becomes less, right? So this is like, if you think about it physically, this is the skydiver jumps out, he's moving very fast, he first opens his parachute. For a while, the skydiver will slow down. As he slows down, the air resistance force shrinks until they're equal and then falls at a constant speed. So it's good to think about the full physics behind the situation. So there's a lot to be learned in each of these problems. I'm going a little bit beyond just answering the question, and I encourage you to do that too. So let's check the answer. Okay, try this one. Again, we're here to learn, so consider each possibility. Notice constant velocity, the net force has to be 0. Which of the following is true about the forces required to maintain the state of motion? 0. All right, stop and answer. Once again, go through all the possibilities. So notice this is a leftward moving object that's accelerating. So there has to be a net force in the direction of motion. Which force diagrams are consistent? This is a net force. This has a net force in this direction. This doesn't, and this has a net force in the wrong direction. So these are all wrong for those reasons. What would be the difference in these two situations? This would be like a frictionless cart being pushed, like a fan cart going to the left. This would be like me pushing a block to the left, but there's some friction. But the pushing force is bigger than the friction force, so it's accelerating. Okay, next. Pause and answer. Once again, pay attention to the language. A westward move is changing speed. It doesn't tell you whether it's speeding up or slowing down, just that it's changing speed. So there has to be a net force, but it could be either eastward or westward. Westward it would be speeding up, eastward it would be slowing down, and none of the must statements well, actually, maybe the must statement does. Could be directed eastward or westward, or be 0. No, that's wrong, actually. So I have the wrong answer. Okay, I didn't read carefully. See, could be directed, yes, or be 0. No, it can't be 0. So it must be either X. So we need to change that to C. Well, anyway, I pressed the wrong button. I got it wrong. We know what the right answer was. It should have been C. Here, pause and do this one. So a leftward moving object, slowing down, coming to a stop, must have a force in the opposite direction. Can't be in that direction, couldn't be 0. That's not true. Okay, check and answer. Why is this false? A leftward moving object experiences unbalanced force, but it doesn't tell us the direction. So then the object moving leftward could be speeding up if the force were leftward, could be slowing down, or supposing the force were upward, the leftward moving object would curve. So there are a lot of other possibilities. So a leftward moving object does not necessarily have an acceleration directed to the left. Think about it, the acceleration is always directed in the direction of the net force. Remember that. Try this one. Moving to the right at a constant speed, the sum of the forces must be balanced. So A works and B works. These would have to be accelerating. They don't work. And yes, this could be true moving in any direction at a constant speed, as could this one. But it says could be moving to the right at a constant speed. So A and B should be correct. Okay, try this one. Again, the language is important, so it's changing speed, but we don't know whether it's speeding up or slowing down. But to change its speed, it has to be speeding up or slowing down, so there must be a force directed either eastward or westward. This doesn't work, we saw last time, because it has or be 0. No, it can't be 0. And so it must be one or the other. It doesn't have to be, it can't say must be eastward or must be westward. It could be either one, but it can't be 0. Also, it says speed. If it said changing velocity, you can also change velocity keeping the speed constant and changing direction. We'll see that later. When an object's moving in a circle at a constant speed, its velocity is changing. That's for the future. All right, try this one and come back. So we know that a leftward moving object which is slowing down, we can tell by the motion diagram, has to have a net force in the opposite direction. So A and E fulfill those. This could not give you an acceleration, none of these. This would, for a leftward moving object, would have to be speeding up. And it doesn't matter whether there's one or two forces. This could be more friction than the forward force. There would be a forward force and a backward force, but since the backward force is bigger, there's a net force in that direction, and the object would be slowing down. You can think of two different situations that would meet these conditions. Also, remember, if you're not satisfied with my explanations, you can go to the help section where the Minds on Physics classroom, the physics classroom will give you help. Okay, let's check our answers. Try this one. So constant velocity, net force has to be 0, right? Constant velocity, net force is 0. Good, done. Mission 4, types of forces. Okay, here we'll talk about all the types of forces. So try to answer this and then come back. I should have told you to draw a free body diagram, so you'll do yourself a great favor if you practice for all these situations drawing free body diagrams. So the truck is skidding to a stop from very high speed. The high speed is important because if it were low, there'd be no air resistance. So at high speed, the truck is going to experience air resistance. It's rightward moving, so the air resistance is going to be opposite the force of friction. So in the Minds on Physics, they'll call it F fric. I just call it FF. Fg is the force of gravity. MOPS will call it F grav. Fn is the normal force. The MOPS will call it F norm. So I use a shorter notation. You should get used to both of them. There's no magnetic force, there's no spring force, there's no tension force, that's usually a chain or a rope, and there's no applied force, that's usually somebody pushing or pulling on something. So this is our introduction to forces and free body diagrams. Okay, try this one, draw a free body diagram. In this case, there's only two forces, and they're equal and opposite. And the force supporting the person is the ground pushing up on the person. We call that a normal force, F norm or Fn. And the earth, right? The force of gravity is the earth pulling down on the person as it pulls on all things. We call that F grav or Fg. They're equal and balanced. So there's only two forces here. Okay, same thing, draw the free body diagram. Okay, to be totally honest, I'm not 100% sure about this one, but I know there's a force of gravity down on the eagle. Since they say glide, an emphasis on glide, I assume that it's moving at a constant speed, but it's hard to imagine there'd be no air resistance going this way on the eagle, but if it's moving at a constant speed, we're just imagining that that it's cutting through the air. But there has to be an upward force to support the force of gravity, and that has to be the air. It's not really air resistance, but we'll ignore that. It can't be the normal force because the normal force is always hard surfaces, and it's none of these. So let's see if I'm correct or not. All right, try this one, free body diagram, and come back. Okay, excuse the funny looking dog, but we definitely have a force of gravity down. We have a friction force because the dog is being pulled and resisting, sliding. We have the normal force of the floor up, and then we have either an applied force or a tension force. But since it says by his dog chain, I'm going to pick the tension force rather than the applied force as being the correct answer. Let's see if that's correct. Okay, here's another one. Same routine, free body diagram. So I hope you're drawing these diagrams. It will definitely be beneficial to you. So here's my simple sled. There's definitely a force of gravity. There's definitely a normal force. And from the description, wind, and it slows down on some unpacked snow, whatever. There's got to be a force of some force of friction. It's not just the wind stopping the person. So the four forces, A through D. Okay, draw the diagram and come back. Okay, simple situation. Book is rested upon a table. We're assuming the table's flat. So the table pushes up on the book. That we call Fn or F norm. And the earth pulls down on the book, causing the force of Fg or the F grav, the force of gravity. In this case, there are no other forces. Okay, same routine. If we ignore air resistance, then the only force is the force of gravity. It's a projectile. And notice we don't ever put velocity vectors or other vectors in the free body diagram, just force vectors. Okay, same routine. Pause and come back with the free body diagram and your answers. So there's nothing about anyone pushing the book. It's just sliding across a level table. There would have to be friction, otherwise they would say it's frictionless. We're ignoring air resistance, so there's Fg, F grav, Fn, F norm, equal and opposite, and a force of friction which will slow the book down. That should be BCE. Is that right? Oh, whoops. Okay, here we are, new one. Do the diagram, come back. Okay, two cables, so I showed two tension forces and the force of gravity. And notice this vector, this one vector, should be equal to those two vectors because it's at rest. And the tension force we call Ft or F10s, Ft, Fg, or F grav. That should be the diagram. Those should be the two forces. Let's check. Okay, do this one. Come back. Okay, notice it's constant velocity, so I want all these forces to cancel. Well, as almost always, there's the force of gravity, the F grav or Fg, the normal force or F norm. This is an applied force because it says a crate is being pushed. And finally, there has to be an equal and opposite friction force because the sum of all forces have to be zero because it's moving at a constant velocity. So let's check our answers. Okay, another one. Pause and do it. Okay, here's the skydiver, constant velocity, so the downward force of gravity has to be equal to the upward force of air resistance. That's called terminal velocity. The parachute is not yet open, so that's going to be at a very high velocity because the air resistance will be greater as the velocity gets higher. Those are the only two forces. Okay, try this one. Okay, it's saying slowly, so we'll ignore air resistance, and I'm assuming it's a constant velocity. So I have these two equal and opposite. So the tension force is what holds the elevator shaft up, and the force of gravity is what pulls it down. So there should only be two forces acting on it. Okay, ready for the next one. So I did say I would put a table of contents at the end, and that's what I've done. Obviously the first one, in other words, I'm going to change to a new video and just stop this one after 4 of the 12 missions. I'll probably make 3 videos. So in case you're looking for where each different mission begins, those are the times. You'll still have to look through them to find specific problems. But there's the table of contents.